Hi everyone, thank you very much for joining. My name is Moshe from the Hebrew University of Jerusalem, and this work is all about tracking users as they browse the web. So the ultimate goal of web-based user tracking techniques is identifying users across websites, networks, browsers, and browser privacy modes. And this practice is used for various purposes. On the negative side, we have real-time targeted marketing and surveillance purposes. On the positive side, we have fraud detection and implementing various protections. And we have things that are in between. So the typical entry point for a web-based user tracking technique is a tracking snippet that is typically written in JavaScript. It runs on the user browsers, it executes the tracking logic, and finally it obtains a device ID that can be used to identify the user. So our work is about analyzing the device-generated TCP source ports for the purposes of tracking users across the web. And since the TCP source ports are not directly accessible via standard JavaScript APIs, we use a tracking server to inspect the source port. So the general flow of our attack is as follows. We have the tracking snippet participate in a series of TCP connections. Some of them reach the tracking server, some of them don't. This is governed by the tracking logic of our attack. The tracking server inspects the TCP SYN packets it gets, extracts the source port, and feeds the tracking logic state machine, which eventually spits a device ID. And this device ID that we extract is based on kernel data, which is up to 128 bits on Linux. It persists across websites, networks, browsers and browsers privacy modes, and even containers in Linux. And I should note here that our attack relies on seeing the device-generated source port, and as such, we cannot track users that hide behind a forward proxy, for example, Tor users, and we cannot track users that access the internet via a NAT router that has a port rewrite policy. So to understand more the attack, we need to understand how TCP source ports are selected. So as you probably know, TCP connections are identified by the famous 4-tuple, the source IP address, the source port number, the destination IP, and the destination port. When the client wants to connect to a service on the internet, it specifies the destination IP and destination port, and it's the job of the operating system to fill in the rest of the tuple. In particular, the operating system chooses the source port number, and it does this via a source port selection algorithm, which receives as input the source IP address, the destination IP, the destination port, and also a state, and outputs a source port number. Now we have two requirements about these source ports. First is a security requirement. They should be unpredictable. And this is to prevent blind TCP attacks or data injection attacks. And the second requirement is more of a functional requirement. We require that the source port will be infrequently reused, because otherwise this can cause delays or failures in connection initiation. So we have an RFC 6056, which defines 5 port selection algorithms with different trade-offs. And our attack targets a particular algorithm, the double hash port selection algorithm, which is implemented in Linux starting from kernel 5.12. So our attack is based on the DHPS algorithm, so I will now describe it. The algorithm state consists of a table of 32-bit integers of length t, which is initialized randomly. You can think of this table as a table of counters. We have 2 cryptographic keys, K1 and K2, which are also initialized randomly at boot time. And we have 2 cryptographic keyed hash functions, F and G, that use these keys. So given a 3-tuple, a source IP, destination IP, and destination port, the DHPS algorithm first selects a counter. It does this by hashing the input tree tuple with the G hash function and the key K2 to produce an index into the table. The next thing it does is compute an offset value using the F hash function, the key K1, and the input tree tuple. And this produces a 32-bit pseudo-random integer, which is important to give the algorithm the unpredictability properties. And to compute a port number, the algorithm takes the counter value from the table, takes the offset, adds them up, does some modulo arithmetic to ensure that the port is in the correct range, and finally, it increments the counter by 1. Now, this algorithm provides reasonable trade-off in terms of unpredictability and infrequent reuse, but it fails to provide user privacy. And in particular, we identified 3 potential security issues that, when combined, can cause a severe issue that will allow us to track users across the web. The first issue is the state of the algorithm is shared, and it is shared across network interfaces, network protocols, so IPv4 and IPv6, and also network namespaces. The second issue occurs when the table length is small, because that would mean that 2 unrelated TCP connections will use the same counter value in their calculation. So the RFC suggests a table length of 10. Linux uses a table length of 256, which is small enough. And the third issue is that the state of the algorithm changes deterministically. So in particular, the counters are always incremented by 1. So now we are going to combine these 3 potential issues into a powerful device tracking technique. So the first observation is that the internet-facing interface and the loopback interface share the algorithm state. And what's so special about the loopback interface is that it has a fixed IP address. So if the client connects to a loopback destination, the counter that will be used in the source port calculation will only depend on the key K2 and would be network independent. So the key idea of our attack is to collect hash collisions of the G hash function for loopback traffic. And what I mean by that is pairs of loopback destinations that use the same counter value in the source port calculation. And these pairs are network independent because they only depend on the key K2. So if we collect enough such pairs, the collection of pairs form a device ID based on that key and based on that key alone. And the lifetime of the device ID is the lifetime of the key, which is until reboot in Linux. So we need a way to find these hash collisions remotely because, again, we don't have access to the source port information from JavaScript. We don't have access to the algorithm state because that's in the kernel. What we can only do is observe the source port directed to the attacker server. So what are we going to do is find these loopback collisions indirectly. So if we find 2 different loopback destinations that collide with the same attacker destination, then we are going to infer that they both collide. But then the question is, how do we find this first collision remotely? So this brings us to the main primitive in our attack, in which we can determine whether some attacker destination collides and uses the same counter as some arbitrary destination. So what are we going to do is have the user device establish 3 TCP connections in a particular order. The first TCP connection will be to the attacker destination. The next will be to the arbitrary destination that we want to test. And the last connection will be to the attacker destination again. So this results in 2 TCP SYN packets reaching the tracking server, which is owned by the attacker. And the middle TCP SYN is generally unobserved. So what the tracking server would do is it would compute the source port difference. And the insight is that if they both share the same counter in the source port calculation, then the delta would be 2, because the counter was incremented twice. And otherwise, the delta would be 1, because they use different counters. So this is how we can remotely detect whether some attacker destination collides with some arbitrary destination. And we build upon this primitive to construct a full device tracking attack. So our attack works in 2 phases. In the first phase, we collect T attacker destinations that uniquely cover all of the table cells. We don't know the actual mapping, only that the mapping exists. And in the second phase, we are going to enumerate over loopback destinations. For each loopback destination, we're going to find its matching attacker destination. And we are going to infer the collisions between the loopback destination themselves. And we stop when enough collisions are collected. So we've implemented this attack. The tracking snippet was written in JavaScript, and the tracking server was written in Go. And our experiments show that this attack is practical over the internet. We tested 2 major browsers, the Google Chrome and Firefox, and found that we get consistent fingerprint across sites, browsers, and networks. We also tested the privacy modes of the browser, so we get consistent fingerprint when you're running the attack from a private tab and from a normal window. The dwell time, the time we require the user to remain on the website for our attack to succeed, is about 10 seconds on Google Chrome. And this depends on the RTT to the attacker server. And on Firefox, this is more. You can find the technical details in the paper. And we also tested Android, but this was a bit tricky because at the time that we conducted the research, there was no device that implemented the DHPS algorithm. So in order to test it, we manually patched the kernel of a Samsung Galaxy S21 device. And with the patch kernel, we were able to test the attack, and we found that the dwell time was around 20 seconds on Google Chrome Mobile. So in February 2022, we informed the Linux kernel security team about the security issue. We got assigned the CVE. We worked with them to patch the vulnerability. And 3 months later, a patch was merged into the Linux kernel. So to conclude, the DHPS algorithm, which is standardized in RFC 6056, is vulnerable to a device tracking technique. We demonstrated our technique on Linux. And I think this research shows that user privacy can be undermined in non-obvious ways. Thank you very much. You can find the extended version of the paper, including the full analysis of the attack, in this link, and also full source code in this GitHub link. Thank you.